Here we are with the first problem in our second problem set from chapter 5. It says a 0.5 kilogram ball attached to the end of a horizontal cord is revolved in a circle of radius 1.3 meters on a frictionless horizontal surface. If the cord will break when the tension in it exceeds 75 newtons, what is the maximum speed the ball can have? So by maximum speed, we're looking for the speed in which the centripetal force is equal to 75 newtons, because if it goes any higher, it'll break. So we're looking for that velocity at a centripetal force of, or a tension force of 75 newtons. And the reason why I said centripetal force there is because in this case, if the ball is attached to the string and no other forces are acting on it, then the tension force should be equal to our centripetal force, or the force required to keep the ball in uniform circular motion. So one thing that we know about centripetal force is that centripetal force must be equal to mass times the velocity squared over the radius of the circular motion. Fantastic. So if our tension force must be equal to our centripetal force, then we can say in this case that 75 newtons must be equal to our mass times velocity squared over the radius of our circular motion. One special thing about this problem is that it gives us, what is given is m, which is equal to 0.55 kg, and radius, which is equal to 1.3 meters. One thing that I like about that's given is that everything is in SI, so I don't have to make any conversions. Now, it looks like, based off of what my equation is, m and radius, mass and radius are required. But what I don't have, what I'm not given, is that v. But as we said, we're looking for v when the centripetal force, or the tension in the cord, is 75 newtons. So I can just go ahead and plug in what I know about mass and radius and solve for v when f sub r is equal to 75. So that's going to be my next step. I'm going to say that 75, or let me get my pen, 75 newtons is equal to 0.55 kg times v squared over 1.3 meters. Awesome. All right, so all I have to do here now is solve for v, and there's a couple of different ways I can do that. I'm going to start off with some simple algebra. I'm going to multiply both sides by 1.3 meters. All right, and then I'm going to divide both sides by 0.55 kg. All right, so on the right side of my equation, I can cancel out my 0.55 kg and I can cancel out my 1.3 meters, leaving me with just v squared on the right. All right, now on the left-hand side, if I go ahead and plug this into the calculator, I have 1.3 times 75. And if I divide that by 0.55, I get roughly 177 meters squared per second squared. All right, if you need to, break up newtons into kilogram meters per second squared, and then just see how that ends up being meters squared per second squared. Now, this suggests that v squared is equal to 177 meters squared per second squared, and where we are here, our units check out. But in order to solve for v, I'm going to have to take the square root of both sides. All right, that's going to give me, which is v isolated on the right-hand side, and then I'm going to have to take the square root of my 177, or whatever's left over in your calculator so you don't have a rounding error. And what I get is roughly 13.3 meters per second. All right, and now if we plug this back into our expression, which represents our centripetal force, then we'll know that the maximum speed that we can have so that our force doesn't exceed 75 newtons is going to be that 13.3 meters per second. Good luck. I'll see you in the next one. This is the second problem in our 5-2 practice set. It says, how large must the coefficient of static friction be between the tires and the road if a car is to round a level curve of radius 125 meters at a speed of 95 kilometers per hour? All right, so this round a level curve is really saying that the car wants to travel in some uniform circular motion along a curve. Now, the thing is that we need some centripetal force in order to maintain the car in its uniform circular motion. That centripetal force, we know, must be equal to the mass of the car times the velocity the car is traveling divided by the radius of its curve. Okay, Well, what is going to apply that centripetal force? In this case, because it's a level curve, we can say that it's on an unbanked curve. This is the vocabulary you'll see most often. And if we have an unbanked curve with a car traveling on it, then the only force that can apply that centripetal force is going to be the static friction force. And if we know an expression that represents static friction force, we can set it equal to our centripetal force. So the expression that's going to represent our static friction force is mu sub s. That's going to be the coefficient of static friction. It's what we're looking for in this problem. And then when we multiply that by the normal force that the car experiences, that is going to be the maximum static friction that we can apply centripetally towards the center to help keep that car on its circular motion path. Okay, so we are given a few things. We're given the radius of curvature, 125 meters. We're also given the constant velocity that the car is traveling along this curve. It's going to be v is equal to 95 kilometers per hour. Now, this isn't in SI units, so I'm going to do a quick conversion to get it in meters per second. You should probably get used to the kilometers per hour to meters per second conversion. It's going to be 5 over 18. And if I multiply 95 by 5 over 18 really quick in the calculator, I should get something like close to 26.4 meters per second. All right, so what I'm given is velocity and radius, but I'm not given mass. So when I look at the equation that I've set up over here, I notice that I do have the normal force as part of the equation, but I'm not given the normal force either. So what I'm going to do is I'm going to break up the normal force into the two terms that make it up. And I'm going to say that my coefficient of static friction times mass times gravity, acceleration due to gravity, of course, is equal to mass times v squared over r, which is, again, just that expression for the centripetal force. And the reason why I say that this can go to this is because we're on a level surface. So on a level surface, the normal force should just be equal and opposite to the force due to gravity. And the force due to gravity is, of course, mass times acceleration due to gravity, hence mg. All right, so this should be the same. Okay, this should be the same, no problem here. We have the coefficient of static friction times mass times gravity is equal to mass times v squared over r. And what's beautiful about this is I can go ahead and cancel out my mass. And that's great because I wasn't given mass. We want to try to find the coefficient of static friction without mass, and now it's gone. So from here, I can go ahead and just move gravity over to the other side, and I can say that the coefficient of static friction must then be equal to v squared over g times r. All right, so just in case anybody's confused, I went ahead and divided both sides by g, which canceled it out on the left, and put it to the denominator in my ratio on the right-hand side. Awesome. I know what all of these are, so I'm going to go ahead and plug in what I know. And just as a reminder, the acceleration due to gravity is, in this case, 9.8 meters per second squared. All right, those units are important. Now, the coefficient of static friction can then be said to be equal to about 26.4 meters per second. This quantity is going to be squared, and I'm going to divide it by the product of 9.8 meters per second squared and 125 meters. In my denominator, the meters per second squared times meters is going to give me meters squared per second squared. That should be the same thing I get on top after squaring the velocity, and that should be perfect because I want to cancel out all my units for the coefficient of static friction. It's just a coefficient after all. So what I'm going to do is I'm going to pop this into the calculator. I'm going to take that 26.4 and I'm going to square it. That's going to give me about 696.4, something around there, meters squared per second squared. Then I'm going to divide it by 125 and divide again by 9.8. That's going to leave me with that coefficient that I'm looking for. In this case, it's going to be about 0.57. So this is equal to this, and that's the coefficient of static friction we're going to need in order for there to be no slip and in order to keep the car on its uniform circular motion along this curve. Thank you. Good luck. I'll see you in the next one. This is problem 3 in our 5-2 practice set, and it says, what is the maximum speed with which a 1,200 kilogram car can round a turn of radius 90 meters on a flat road if the coefficient of friction between tires and the road is 0.65? Is this result independent of the mass of the car? Now, if you're coming from the previous problem, you'll know very quickly that the answer to that last part of the question is yes, it is independent of the mass of the car. The mass of the car doesn't matter on a flat road because the only thing that's contributing to the centripetal force on the car to maintain its uniform circular motion is the static friction force. And we know that when we equate the static friction force, which is mu sub s times m times g, to the required centripetal force, or mv squared over r, that our masses cancel. We did this in the previous problem, and we found that mu sub s times the acceleration due to gravity would then be equal to v squared over r. And in this case, if all we're looking for is the maximum speed, then we can go ahead and very quickly solve for v, or isolate v, and that would require us to multiply both sides by r, which would give us r times the coefficient of static friction times the acceleration due to gravity is equal to v squared. And the only other algebraic step we need to take from here is to take the square root of both sides, and then we'll be left with v is equal to the square root of r times coefficient of static friction times the acceleration due to gravity. All right. Now, what's great is that what we have given is the radius. Okay, so r is equal to 90.0 meters. The coefficient of static friction is equal to 0.65. And then g, which is kind of assumed, in this case is 9.8 meters per second squared. And notice that those three variables are exactly what we have underneath the radical, which we have set equal to v. So we can go ahead and plug in what we know and then solve for that maximum speed. So that said, I'm going to go ahead and do it right here underneath my given. I'm going to say that the square root, and I might need a little bit of a longer square root bar, the square root of 90.0 meters times 0.65, which has no units, it's just a coefficient, times 9.8 meters per second squared. Okay, these three terms underneath the radical, these three factors underneath the radical are going to ultimately give me units of meters squared per second squared. But when I take the square root, it's going to give me meters per second. So let me go ahead and plug that into my calculator really quick. 90 times 0.65 times 9.8, about 573.3. And if I take the square root of this, I should have roughly 23.9 meters per second. And that's going to be about the maximum velocity that I can take this turn at. Good luck, and I'll see you in the next one. This is the fourth problem in our 5-2 practice set. It's a bit of a long read. Let's get started. It says, a jet pilot takes his aircraft in a vertical loop. Luckily, we have a figure here to help us visualize what we mean by vertical loop. And part A says that if the jet is moving at a speed of 840 kilometers per hour, at the lowest point of the loop, determine the minimum radius of the circle so that the centripetal acceleration is the centripetal acceleration at the lowest point does not exceed 6 Gs. All right, so really quickly, I'm going to go ahead and write down what we're given. We're given velocity, which is 840 kilometers per hour, and we're given acceleration, which is equal to 6.0 Gs. Now, I'm going to go ahead and multiply both of these given values by a quick factor to turn them into SI units. For the 840 kilometers per hour, that's going to be a factor of 5 over 18. And for the 6 Gs, that's going to be a factor of 9.8. All right. So when I go ahead and calculate the conversion here, 840 times 5 over 18, that gives me something like 233 meters per second. And when I calculate the conversion for my acceleration, that should give me something like 58.8 meters per second squared. Fantastic. Now I have everything that's given in SI units, and now I need to consider what relationships I need that are relevant for this scenario. Well, I know, of course, that Newton's second law is always relevant, and that tells me that F is equal to mass times acceleration. Another relevant equation here would be, of course, the required centripetal force needed in order to keep this aircraft in uniform circular motion. That's going to be F sub r is equal to mv squared over r, that lowercase r being the radius. Now, I think we can go ahead and put these together, cancel out mass, and then we'll have a relationship equating acceleration to velocity over radius. That said, if ma is equal to mass times v squared over r, then I can go ahead and cancel out my mass, and then I'm left with the relationship that my centripetal acceleration must be equal to v squared over r, and that's exactly what I want because I have acceleration and I have velocity, and now I just need to solve for the radius. Fantastic. Let me go ahead and set up this equation in terms of acceleration and velocity, which is just going to be r is equal to v squared over a. Let me go ahead and plug in the values that I have for v and a, and then we'll very quickly solve for r. R is going to be equal to 233 meters per second. This quantity is, of course, going to be squared, and we're going to divide that by 58.8 meters per second squared. All right. So my units on top are going to be meters squared over second squared, and my units on bottom are going to be meters per second squared, and I should be left with just one-dimensional meters, which I can apply to my radius. All right. So really quickly, let's do this in the calculator. That 233 squared divided by 58.8. That should give me something very close to 925.9. And that's going to be meters. So we're going to assume that this is our answer to A. This is going to be the radius that would be required in order to maintain some uniform circular motion given these other values. Fantastic. Now let's look at what B is asking. It says, calculate the 78 kilogram pilot's effective weight or the force that's being applied to him from the seat of his plane. All right, so let's go ahead and zoom in here actually, because this is more of a conceptual problem. We know already based off of the math we just did that the centripetal acceleration that the pilot is going to be experiencing from the plane at this point, or really at any point, is going to be basically 6 Gs. All right. Now, the thing about it is that at this point, gravity is also forcing him downward. It's forcing him downward onto that seat, and that seat is also going to be giving a equal and opposite reaction based off of that force due to gravity. So what we can say is that his acceleration due to gravity at this point is going to be 1 G. So what that's going to do is that's going to add to the 6 Gs he's already experiencing due to the centripetal acceleration that the plane is providing onto him. So at this point, we can say that he's going to be experiencing an acceleration of 7 Gs or a force of 7 mgs. And hopefully that makes sense because F equals ma. So all we're going to do is we're going to throw in the mass of that person. So that mass here in this case is the mass of the person, which of course is the 78 kilograms. All right, so we can go ahead and calculate that, but it's just 7 times mass of the person times the acceleration due to gravity. And then part C is asking at the top of the circle. So it's going to be the same kind of thing, except in this case, the force due to gravity is going to be pulling him away from the seat. All right, it's still downward. So then instead of the adding 1G, we're going to be subtracting 1G to the force between him and his seat, and that's going to leave us with 5 mg. All right, feel free to comment down below if you have a question about that last part. I'd love to elaborate a little bit more fully, but for now, good luck. Think about that last B and C part. I'll see you in the next one. Here we have the 5th problem in our 5-2 practice set. It says a proposed space station consists of a circular tube that will rotate about its center. The circle formed by the tube has a diameter of 1.1 kilometer. What must be the rotation speed if an effect nearly equal to gravity at the surface of the Earth is to be felt? Now, I see that it gives us 2 things here. First off, as far as what's given, as far as what's given, I see that the radius is given. And so really quickly, 1.1 kilometer is just 1,100 meters. If I take half of that, I have 550 meters for my radius. Another thing that's given is my centripetal acceleration. That's going to be equal to 0.9 G, and in this case, that's just going to be 9.8 times 0.9. That's going to give me about 8.82 meters per second squared. Now, the question is asking what is the frequency, because it's asking about revolutions per day. Now, if we're in SI units, then when we solve for frequency, we'll have revolutions per second, and then we're just going to have to convert that to days. Now, to get started, let's go ahead and write our relationship between the centripetal acceleration and the velocity and radius of uniform circular motion.
So we have that the centripetal acceleration is equal to v squared over r. Now, we don't know v, but we do know a and r. So really quickly, I can solve for v, and then we're going to use that v to find the frequency of this circular motion. So I'm going to go ahead and plug in my 8.82 meters per second squared. And I'm going to set that equal to v squared over r, but instead of r, I'm going to go ahead and write my 550 meters. Now, if I multiply both sides by 550 meters, then I'm going to cancel it out on the right side. And then what I'm going to have left on the left side is 4,851 meters squared per second squared. Now, that seems like a lot, but remember, in order to find the actual velocity, we're going to need to take the square root of both sides. That gives us about 69.65 meters per second. That's going to be our v. Okay. So if the velocity is about 69.65 meters per second, what relationship can we use to maybe find our frequency? Well, there's this one relationship. It's going to say that our velocity is going to be equal to the circumference of our circular motion times the frequency. Okay. We don't have the frequency, but we do have the velocity, and we can derive the circumference because we know that the formula for circumference has to do with the radius, and radius is one thing that we do have. So if I'm looking for circumference, then I'm just going to say that's 2 pi times the radius. So 2 times pi times 550. That gives me about 3,455, let's say 0.75. If I plug that into circumference here and I plug in my velocity, 69.65 meters per second is equal to about 3,455.75 meters times frequency, then the only thing I need to do to find frequency is divide both sides by that circumference. So 69.65 divided by 3,455.75. Looks like I get something about 0.02. We could say 0.2 here if we wanted to go that far. Best to keep a few extra decimals if you're still working. From here, we're going to have to convert this to revolutions per day, because remember what I told you is that when we find frequency, it's going to be in revolutions per second. So the conversion here is just really to find out how many seconds are in a day. You should probably have memorized how many seconds are in an hour. That's 3,600. So from there, you just have to multiply 3,600 times 24. That's going to give you 86,400, and we're going to go ahead and multiply that by our answer here. In this case, that's going to give me something like, so of course, we're going to multiply this by 86,400 seconds over 1 day. That's going to leave us with revolutions per day. Our seconds cancel, and we're left with about 1,745.28 revolutions per day. Good luck, and I'll see you guys in the next one. This is the sixth problem in our 5-2 practice set. It says a pilot performs an evasive maneuver by diving vertically at 270 meters per second. If he can withstand an acceleration of 8 Gs without blacking out, at what altitude must he begin to pull his plane out of the dive to avoid crashing into the sea? All right, first off, we're talking about acceleration, velocity, and radius here. So we have a relationship for that. So we have the relationship that centripetal acceleration, which we know, must be equal to this velocity squared over the radius of your circular motion. So what this question is asking us to do is to kind of assume that the pilot is going to be traveling in some circular motion. And one thing that we need to know about the circular motion is that if there's a point when his velocity is perfectly downward, and that's kind of what it's hinting towards when it says diving vertically, the only point on this circular motion where his velocity would be downward if we're moving, say, in this direction, is at this leftmost point here. So this leftmost point is the only point that would have a velocity vector that's perfectly downward. So we want to find the velocity when it's perfectly horizontal, because he started off in a vertical dive and he wants to kind of level out so that he doesn't crash into the sea. So the point is that if he started here and he's ending here, then the difference as far as the XY axis is concerned is just one radius height, right? Because if he's here and then from here, the difference in altitude is just equal to the radius of this circle. All right, so hopefully that is something that you can visualize here. And so if we find this radius, we'll know how high above ground he'd need to be in order to level out before hitting the ground. All right, so let's plug in what we know about this. And sometimes it's actually easier to rearrange your equation before you actually start plugging in. Since we're looking for r, I'm going to rearrange my equation for r. I'm going to multiply both sides by r, then I'm going to divide both sides by acceleration. That's going to give me r is equal to v squared over a sub r. Now we know what our maximum a sub r should be, and that's how we're going to find radius. So I'm going to go ahead and plug in 8 g's for a sub r. And I'm going to also plug in 270 meters per second for velocity. This quantity needs to be squared. And then 8 g's is just 8 times 9.8. So if I plug that in the calculator real quick, 8 times 9.8. That's actually going to be 78.4 meters per second squared. All right. So if I square my velocity, then I will have about 72,900. That's going to be over, and of course that's meters squared per second squared. And that's going to be over my 78.4 meters per second squared. If I go ahead and divide by my acceleration, I should get a radius of about 929.8 meters. All right, so the units on the right-hand side here were meters squared over second squared, all divided by meters per second squared. That cancels everything out except 1 unit of meters. So then, yeah, we have a radius now of just meters. So then that's the answer. At what altitude must he begin to pull his plane out of the dive to avoid crashing? It's going to have to be 929.8 or at least 930 meters above sea level. Good luck. I'll see you in the next practice set.